In this chapter, we're going to introduce the normal distribution, or normally distributed random variables, and that's a continuous distribution. In order to understand what a continuous distribution is, let's look at what we've looked at so far in this course, which are discrete distributions. So discrete distributions are where the set of possible values that the random variable can take is a discrete list. So for example, if x was the number of heads when a coin is flipped 10 times, then we know that the set of possible values that x can take is 0, 1, 2, 3, all the way up to 10 heads. And the reason why this is called a discrete list is because if you look at a value in between those set of possible values, so for example 1.2, there's no probability at 1.2. The probability of x equaling 1.2 is 0, just because it doesn't make sense to say you have 1.2 successes. So a binomial distribution is an example of a discrete distribution. Well, we're going to look at a continuous distribution called the normal distribution. And a good example of understanding what a continuous random variable is people's heights. Now you know that if x is people's heights, then you know that x can take any number along the number line within a sensible range here. So for example, we could have someone with a height of 180 centimeters. That's perfectly reasonable. And we could have someone with a height of 190 centimeters. And what makes this a continuous random variable is it would make sense for someone's height to be anywhere on the number line between 180 and 190. So for example, we could have someone with a height of 187.2, or we could have someone with a height of 107.21596 centimeters. Okay, so that's what makes it a continuous random variable. In order to help us understand the normal distribution, we're going to introduce these two terms, the mean of the distribution and the variance of the distribution. Another word for mean that you might hear is the expectation of a distribution. So we don't need to worry too much about how to calculate these terms. I just want you to get an intuitive understanding of what they mean. Well, the mean of the distribution is very similar to the sample mean of a set of data. It basically tells you, on average, what would you expect our random variable to be. So just intuitively, if x was the number of heads when a coin is flipped 10 times, you're doing 10 trials and the probability of success on each trial is a half, so you'd expect x to be 5. You'd expect to get 5 heads on average. The variance of the distribution tells you how spread out the probabilities are amongst the x values. And we don't need to know this formula, but if you do further maths, you'll see this formula next year. The formula for the variance of the binomial is np 1 minus p, but again, you don't need to know where that comes from. So if you worked out the variance of this distribution, you could work it out as 2.5. And similarly, just like we would normally do, you can actually work out the standard deviation of this distribution. And you could work that out by doing the square root of the variance, so square root of 2.5. And the standard deviation of this distribution is 1.58. We also need to understand what the terms parameters of a distribution mean. So here we've got a binomial, x follows a binomial 10, 0.5. These two numbers here inside the brackets are called the parameters of the distribution. And the parameters of the distribution change the shape of the distribution. So for example, I could reduce the probability of getting a head to 0.2, make it biased against heads. So here we've got a binomial 10, 0.2 distribution. And again, we could work out the mean or the expectation of this distribution. If you've got 10 trials, the probability of success is 0.2 at each trial. You'd expect x to be equal to 2 successes. And the variance of the distribution, again, we could work that out using the formula that we did before. And the variance of this distribution is 1.6. And the standard deviation is the square root of 1.6, which is 1.26. So you can see that this distribution here is less spread out than this distribution here. And that's reflected in the fact that the standard deviation and the variance is smaller for this distribution than it is for this distribution. So let's take a look at this normal distribution then. Let's say that x follows a normal distribution, and we just say n, where n stands for normal, just like b stands for binomial. And the normal distribution has two parameters, mu and sigma squared. So mu is the mean of the distribution, and sigma squared is the variance of the distribution. And we'll take a look at the effect of these two parameters on the shape of the distribution in a second. So what we could do is we could plot what's called the probability density function curve. So in the middle of the curve, so we've got our, on the x-axis we've got our values of x that x could take, and it's continuous along the number line. And the curve is symmetrical about x is equal to mu. And it turns out actually that the mean and the median of the distribution is mu. And what that means is that half the probability is to the right of mu and half the probability is to the left of mu. So the probability of x being greater than mu is a half, and the probability of x being less than mu is also a half. So next, let's have a look at how to use this curve in order to find probabilities. It might be worth noting that actually you could plot this curve in your calculator. If you plotted the curve y equals 1 over the square root of 2 pi sigma squared e to the power of minus 1 over 2 sigma squared x minus mu squared, then you would get a curve that looks like this. And thankfully we don't need to be able to work with this curve, because our calculators will always calculate these probabilities for us. So let's suppose we had x as a score of a random person in an IQ test, and x follows a normal distribution with mean 100 and variance, so sigma squared, equals 20. So what that tells us is that the mean of the IQ scores is 100. So the distribution is centered about 100, and it's symmetrical about 100. And if we wanted to work out the probability of someone's IQ score, for example, being between 110 and 120, what we would do to work out that probability, so let's write that down. So the probability of x being greater than 110 and less than 120, we would actually work out the area underneath this probability density function between 110 and 120. And we don't actually need to know how to do that, because our calculator can do that for us. And we'll look at how to do that in a second. But we could work out that probability, and it's the area between 110 and 120. And similarly, if we had x is the height of a random person in centimeters, and we know that the mean of the distribution is 180, and we know that the variance is equal to 10. If I wanted to plot this curve, I know that 180 is in the middle, and that basically means that the probability is centered around 180. These round about 180 is where most of the probability is. If I wanted to work out the probability of someone being less than, let's say, 140 in height, then I could work out the area underneath this curve all the way down to minus infinity. So this normal distribution curve actually goes from minus infinity up to infinity. Now, you might think that doesn't make sense because you can't have someone who's like 1 centimeter high. Well, we don't worry too much about that because this graph goes down really, really quickly. So the probability around about someone being 1 centimeter high will be like 0.000000001. So it's kind of negligible. So probability of x being less than or equal to 140 is the area to the left of 140. And it's worth mentioning at this point that actually, if you had the probability of x being equal to 140, so what's the probability that someone is exactly 140 centimeters tall? With a normal distribution, with a continuous distribution, we actually say that probability is 0, because the kind of intuitive understanding of that is someone's not going to have a height of exactly 140 centimeters. It's going to be 140 point something. Okay, and similarly, that works for every single specific value of x. So, for example, the probability of x being equaling 180 is also 0. Well, what the effect of this means is it means that it doesn't matter whether you use a strict or not strict inequality. So here, this would be exactly the same as saying what's the probability of x being less than 140, because the probability of someone having a height of exactly 140 is 0. Finally, let's have a look at what these parameters mu and sigma squared do to change the shape of the distribution. So let's use this example, sticking with people's height. So x is the height of a random person, a random variable, and let's say that we know that height is normally distributed. So that means that x follows a normal distribution, and the mean is mu, and the variance is sigma squared. And let's say that we're interested in what's the probability of a random person having a height of less than 170 centimeters. So here I've got the normal distribution curve, and the value of b, unfortunately I can't use mu, is the mean of the distribution. So first of all, let's have a look at what happens when I change the mean. So at the moment I've got it set up for the national average height, which is about 180 centimeters. And in order to work out the probability of someone having a height of less than 170, we could work out the area underneath the curve to the left of 170 and find out what that probability is. And you can see here that this probability is going to be less than a half, because we know that half the probability is to the left of 180. So if we reduce the mean, so say for example I thought that actually I'm going to pick a person from a primary school, so I'm reducing the mean to say 160. So I think the mean height is 160 at primary school. Then I can see that the area underneath the curve to the left of 170 has gone up, which is what you would expect if I went to a primary school and changed the mean to a smaller number. And you can see here that the area here is actually more than a half this time. So then when I change the mean, it basically moves the distribution left or right, but it keeps the same shape. Similarly, A here is my standard deviation, and you can see that when I reduce the standard deviation, the probability in the tails reduces. By that I mean the probability becomes more centered around the mean, closer to the mean. So if I wanted to work out the probability of someone having a height of less than 170, when I reduce the standard deviation, the area to the left of 170 decreases. Okay, so that's the effect of variance and mean on the distribution. One shifts it along, and one changes how spread out it is.